Good stuff. Okay, cool. Today, I want to start talking about test benches and verification.
Let's go.
And I will also be touching just a hair more on like ready valid. So first, yeah, I think this will be good. So first, I just want to show you this module. What does this module do?
It adds.
Yeah, adds two numbers. But how do we know that this actually works? Well, what you're supposed to do is you're supposed to write like a test bench. You're supposed to write some sort of additional bit of code that verifies that this works. And Digital.js Online is really great because you can put this module into Digital.js Online and you can go and like click the different buttons on the screen and you can kind of somewhat prove to yourself that the module works. But it would be nicer if instead of loading this code up into like a GUI and then clicking like the random buttons, it would be nicer if instead you could write like an actual like set of like instructions and commands and like input parameters into this and then test now the output that's coming out. And that is what a test bench is. So in Verilog verification, we will write test benches. And so first, I want to, let's write a simple test bench for this adder module together. The first thing, so what tool I've already been using in like in-class demonstrations has been Yosis. Yosis is used for synthesis, the act of converting from a Verilog module into a netlist. But instead, we will be using a different tool, which will be a simulator. So in this lecture, we will use Verilator. This is my personal favorite open source simulator. There are a bunch of different simulators out there, but I'm going to use Verilator. Note that this is going to be a different flow than actually what the like tests that you are given in your homework is. I personally just like using pure Verilog in my test benches, and I feel like this is kind of more common. At least when I was at Intel, all of the test benches were written in like just pure Verilog. But I know there's been a recent push to write test benches in like Python and using CocoaTB. CocoaTB, that's what all of your tests have been using. It's a cool like Python wrapper that actually can call Verilator and it can call Icarus to do like small little like commands. But what you can do instead is you can just write like a full Verilog module and pass it into Verilator and it will simulate it all just entirely using Verilog constructs. Okay, yeah, question?
What's the difference between a simulator and something like a synthesizer?
Yeah, okay, so I'm hoping that this lecture will be a good demonstration of what a simulator will do. So I'm going to, first I'll just run Verilator on this module here. And the way that you run Verilator is you type in Verilator, you should have it already installed on your code space. And then after that, then you do -- binary, and this will create an executable for us to run, because the kind of whole idea with simulation is instead of converting this file into like a netlist, instead what this is going to do is it's going to convert it into an application for us to run on our computer. So it actually converts it into an application. So if I do -- binary, and then I can go and pass in this file, you can see I called it tb.sv. It's not actually a test bench yet, but if it was a test bench, you can call it tb.sv. So okay, there we go. So now I'm running Verilator, and you can see it's running a whole bunch of stuff. Actually, if we look closer at what this is, can anyone see like what command is actually being run right here?
G++.
Yeah, G++. So there are all sorts of different types of simulators out there, but specifically what Verilator does is Verilator will actually take in Verilog code and it will convert it into C++ code. Then by using -- binary here, G++ will be automatically called on the generated C++ files. So that is what Verilator does. Verilator will take in Verilog files and will convert it into C++. And then you can then create an executable for that. So okay, cool. So now it looks like we've just created the executable. So now I can run it. It was put inside of the objdr directory here. And you can see the output is VTB. And that's just the default like name. So okay, VTB. So I can now run this, and we can see that actually like nothing very interesting happened, because like this is just a hardware module. And ideally, what a simulation should have is like drivers, and like it's something that drives the inputs, and maybe tests that test the output. First, let's just do a simple hello world, just to make sure that it is actually doing something. So I can go and run initial. So here, this is an initial block. It has like the same sort of syntax as like an always block, like an always comb or an always ff, except now it's just called initial. And initial is generally only used for simulation. So now what I can do is I can go and put a print statement in here. And the most basic print statement is display. And so now I can say hello world. Okay. And yeah, note that I'm not touching any of these wires here or anything, but like I can just add a print statement. And so now I can rerun Verilator. And the one problem with Verilator is actually it takes kind of a while to compile. But okay, there we go. So I compiled it and ran it. Now it says hello world. Cool. Yes.
You're saying Verilator uses C++. What do other like simulators do?
Most other simulators actually will convert to an internal language. That's like hidden. And like what Icarus's internal language, I think it's called like VVP. So you may see that it generates like VVP files for you. If you look if you look in like the run files of, sorry, am I saying this wrong? Icarus uses VVP. So if you look in like the run directory for Icarus, then you'll see the .vvp files. Yeah. And then other simulators, yeah, they'll use their own thing. Yeah.
And then also, so Verilator, Verilog and System Verilog and all these hardware descriptive languages, like they're not really sequential in the language description. So how
Correct.
is this here like actually converted to something like a sequential language that's executed like C++?
Correct, right. So yeah, so the hardware, obviously, like it's actually just like supposed to be a bunch of connections of wires and things. But C++ is run sequentially, one line after another. And it is really just up to the simulator engineer's job to figure out a way to convert the Verilog into C++ in a way that when you run that C++ program, it does properly simulate it. So that is also up to the developers of the simulator. And I actually am not really an expert on every single step of the simulation. Maybe at some point I can do a lecture on that. But you can basically just imagine Verilator as just a black box where when you run it, it will just magically kind of simulate the circuit perfectly. So okay, cool. So that is now a hello world. If I want, I can add a little delay now. And the most basic way to do a delay is to put a hash symbol and then specify how long you want the delay. So I can say delay for 1 nanosecond if I want. Then I can go and print another thing. And if I want, I can now print out the time. So I can say something like this. I can do %t for time, and then I can do $real time. And this real time is it's a system Verilog, or it's a Verilog construct that will produce the time elapsed as a float. And then this %t, this will format it as like proper time. Display uses like the same sort of like printf capabilities as like C++ as well. So we can do.
For me, I think the %t inserted a tab.
Oh, you're right.
And then it just displayed the number at the end.
Are you sure?
Yeah, I think it's %d or.
Is it D?
Yeah, generally it's
Because it printed a tab and then it just appended real time.
Oh no. Yes. No, this is correct. I think.
So you don't need to use
So
that.
it just has a bunch of spacing for some reason?
Oh, so it's kind of like Python.
I think. Hold on. I think you would want to do %0t. Hold on. Actually, might be. Yeah. Okay. So what was happening is it was leaving a bunch of extra spaces. Okay, yeah, so let me rephrase that. So you can see, so if I ran this, so %t and in real time, you can see it does, in fact, print out the, it prints out hello world. Now it prints out the time elapsed, but you notice that it actually adds a bunch of white space here. That is to leave room for the largest possible float value. Yeah. If you want to get rid of all of those tabs, you can put a 0 right there, and that will eliminate all of the incoming tabs, which is actually backwards, I think, from C++. I think C++ will add tabs if you put a 0 there. Yeah, which is funny. But
Or actually, I think it adds zeros if you
Right,
put
it
zero, and
right.
it adds spaces if you put a space.
yeah, yeah.
Does it, wait, so it prints the time
Yes.
after, like, the display is printed, or like what time is it referring to, like real time?
Yeah, great question. Okay, so
So like as soon as the program is run, or like,
so maybe you're used to like time referring to like the time on my computer's like clock. Instead, what this time refers to is the amount of time that has elapsed inside of this simulation in terms of like number of like, ticks you can think of. You can think of like as the simulation increases, like it takes a long time to run these simulations. Even simulating just like a single second could take potentially like a few minutes. So what we're saying here is like, here we're delaying by 1 nanosecond, then we go and print out the time. And I guess the time is being formatted in terms of
200
picoseconds.
nanoseconds per second is pretty bad.
Where do you see that?
Speed.
Oh yeah, that's pretty funny. Yeah, so you can see it's like, it's very, very slow. So that's why it can potentially take like a week to boot Linux on like a CPU simulation, which is funny. Okay, so now, I'm now going to run this. There we go. So we can see that I at first print out that it took 0, or first we're printing out at time 0 in our simulation. Then we print out at time 1 nanosecond. Here we're printing out time at 2 nanoseconds. Here time at 3 nanoseconds. Hold on for just a second. So I will also throw in this line right here. I think this, you can kind of ignore exactly what this line does, but it basically will now format it as a little bit more human readable. And instead of nanoseconds, maybe we'll delay by milliseconds instead.
So are these dollar and hash statements only valid inside of initial blocks?
No,
Where
they are
they
not.
valid?
They are valid anywhere.
When do they get run if you just put it in a module?
They are run as soon as they reach that line in the code.
Oh, I guess it only
'Cause this is an
matters if
initial
it's
block.
simulate. I guess it only matters if it's being simulated.
Right. Okay, I'm gonna move on. I didn't want to spend too much time on time. But yeah, so we are able to control the time, and if we want, we could also go and create like variables and like change the values of the variables. What I'm actually going to do though is pull out of this module, and I will go and create a separate like, test bench module to now see if we can try to verify this adder. So I will now create a new module, and I'll call it TB. And this new TB module probably doesn't need any input parameters, so I'll just leave that blank. And there we go. So this is our module. And then I'm going to go and instantiate this adder inside of this TB module. And also, I'll pull down this initial block. So okay, so I'll instantiate this adder. And what I like to do is just copy and paste this in, just make sure I'm not messing anything up. Okay, and in test benches, the naming conventions of things like aren't as important as the actual RTL. So if we want, we can just do dot. We can just grab all these. Okay, there we go. Also, note this syntax. I've used it a few times, but I don't think I've explicitly mentioned it. So this syntax right here, where I just do dot and then the name of the port, this is the exact same thing as just doing this. The only requirement is that like the name of the port in the module must like exist. Like it must have a match with the port of the module you're trying to instantiate. Does that make sense? So if like A of I exists in this module, and then I just do like dot A of I, then it will automatically go and connect this A of I to the adder A of I.
So you could put it in any order and it would.
Oh, so mainly, like I can get rid of this like parenthesis part. That's what I'm saying. So I'm getting rid of this.
Does it use the name or does it use the index if you don't specify like the argument?
So because it's a dot, it uses the name. Yeah.
So like if you put BI before AI when you're instantiating,
Yeah.
no problem will happen?
This would also work. Yeah.
Okay.
It would connect them up the same way.
It would connect them the exact same way. I will say that if you, now this is very slight change, if you get rid of this period right here, if you get rid of this period, then it will look at the order of the ports. But if you have this period, then we'll go off of the names of the ports.
Oh wait, so you said without the period it goes in order.
Correct.
Oh wait,
Yeah.
that's so much better.
And you should never connect ports like this. Yeah.
Oh.
You shouldn't do it this way because generally your modules will have like hundreds of ports,
That's-
and so it's really like confusing. Okay, I'm getting a lot of questions. Yeah, Marco.
I have that.
Okay, Todd.
Do you prefer going line by line with the inputs or putting everything?
Say it again.
Do you prefer the inputs all in one line or like in separate?
Oh, I always do it one by one, and I've never seen anyone do it all in one line, other than everyone in this class for some reason. So I don't know like what professor is telling you to do it like this, but
We all just picked it up from 100.
yeah, I guess in 100 you're instantiating like tons of modules, so that makes more sense. Generally in a module, you're at most only like bringing in maybe like 5 other modules at once. So, but in like 100, I bet you had to like instantiate probably like 30 modules. So it probably makes more sense to make one line in CSE 100. But anyways, okay, I'm gonna keep moving on. This is not what I wanted to talk about. Okay, so cool. We have now just instantiated our adder. A common naming convention, probably the only important naming convention in test benches, is for the name of the module that you are trying to verify. Generally, people call this DUT, design under test. So we would say that this module right here is our design under test, or it's our DUT. Personally, I actually disagree with that. And I actually just always leave it as the name of the module that I'm trying to instantiate so that I like know what I'm working with. I don't like that it's just like, oh, like DUT. But you can do either one, and probably people will be more happy with you, like in the job interview, if you use DUT. But me personally, I actually like that. Question.
So it really doesn't matter because I've always in 100 I was making my test benches. I would always use UUT or like any kind of
Yeah,
other-
unit under test, that's also fine too.
So it really just doesn't matter.
It actually does not matter at all, yeah. Generally, people like to call it, yeah, DUT.
I always imagined that it did matter for some reason.
It actually doesn't. Okay, good. So now we can go and drive each of these inputs. It sounds like, okay, sounds like we have some experience in writing test benches from 100, so I'll go a little bit faster. So, okay, let's go and modify these variables. I will also get rid of real times. Okay. So, yeah, what I will do now is maybe we can assign these to like, I don't know, 3 and 4. Okay, and now we should imagine that if we just now wait for the data to propagate a bit, so maybe we can wait 1 millisecond, then what we can do is assert that C out is equal to maybe 7. This is what we would imagine, right? So if we have 3 and 4 passing into our adder module, then there should be some amount of delay as like the signals propagate through our adder, And then finally, yeah, maybe 1 millisecond later, we go and check, like, was the result equal to 7 like we expected? Okay, cool. Another thing is we can end our simulation. Sometimes, depending on your simulator, you don't need to put this line, but in this case, I will put it, it's good practice. I'll put a finish statement, which will officially end the simulation. So once the simulator reaches this line, it will stop running things, okay? So now I will go and run this. And you can see it's taking a little bit longer because now it has to compile for timing constructs, okay? And I did not add any print statements, but you can see it did successfully go, it worked because we did not get any assert errors. If I want, I could say something like info, which is another display alternative. I could say success or something. Good.
Wait, is info just a synonym of display?
You'll see. So now we can see
Whoa.
here's an info, and what info does is it will print out the amount of time that has elapsed. It will print out info, so if you wanted, you could search for all of your info statements in your log. It will also print out the name of the module, the name of the file it's currently in, and the line of the file, and it will print out the name of the module. So yeah, info, very useful. There's also warning, warning and error and fatal. And you can imagine how they work. Good, so now maybe what we'll do is we'll add a couple more variables, but what would next be nice is if we could write this out to a waveform. So I'm going to now add, maybe let's add, I don't know, 6 and 2. So what should this be equal to now? Okay, 8, good, cool. And maybe let's do one more, I don't know, what numbers should I do?
Negative.
I won't do negative. Let's do 9 and 11, 12. And that should be 21. Okay, actually, let's fail. Let's say it's equal to 20. Good, okay. So now, if I go and simulate this, we should see that it should fail. It should say assert failed. Let's see what happens. Okay, I guess it succeeded. What's going on? I actually don't know why that happened.
Are assertions enabled?
Ah, thank you. I don't know how you, that is exactly the issue. Yeah, so by default, Verilator does not enable assertions. The way you do that is with -- assert. Oops.
Oh, that's funny. Mine is doing assertions by default, though.
Oh. Okay, that is very odd. There we go. So now we can see that the assertion failed. Good.
Wait,
Cool.
what's the command to add an assertion?
Yeah. --assert.
Okay, thank you.
Yep.
Oh, actually, no, never mind. It's because I had a fatal
Okay.
message.
Oh, right,
That
right.
also kills it when you call it.
Yes, it does. Okay. Good. So now, okay. Well, now it's dang it, we have now there's a bug now. And it's maybe this is some really long test bench. Maybe it's been running for 5 minutes and it finally just failed. You're this sucks. It's okay, well, generally what you do is you could poke around in your test bench and try to just guess what's going on. But more likely what you would do is you would want to dump out all of the nets to a dump file, like a wave dump, so we can see at every time step what every single net, so what every single variable was set to. And the way that we do that is first, just on our first initial, is we want to add a dump file. So I will call this dump.fst. There are a few different types of dump files. Actually, let's do VCD instead. VCD is has an IEEE specification. VCD was originally the most basic format for storing waves. And you can actually open it and see it. And okay, and then I will also do --trace here. This will enable tracing. I also need to do dump vars. This will specify that I want to dump everything. And I think that is good. Okay, so now, so this will dump all of the variables to this file called dump.vcd. And you can see I had to do --trace in my command in order to do this. So now when I go and run, and you can see now it's taking extra long to compile it. It's because now it has to compile all of the code necessary for creating VCD files. So Verilator, yeah, can take quite a while to build. But then once you build it, it's very fast. So there we go. So I have successfully created a FST file. What? Why did it? Okay, that is.
By default, just.
Yeah, you might have like some of the automatic things.
Do you have to?
Oh, no,
do
no, no,
dump
sorry.
file after?
I just misread it. Yep, so I think dump.fst just existed from last time. So here is dump.vcd. And, oh, yeah, I guess I can open it in, oh yeah, I can open it in Surfer. All right, so that's cool.
What's the difference between VCD and FST?
Yeah, I'll tell you in just a second. So here we can check out our VCD file. And good, so now we can see, okay, yeah, so looks
What
like it
application
seems to
do
be
you
working.
recommend for VCD?
The same, so Surfer.
Surfer.
Either Surfer or I personally use GTK Wave.
GTK, that sounds friendly.
Sure, GTK Wave or Surfer, they're both fine. Yeah, so here we can see that it seems to be working. So okay, so 3 plus 4, 7, okay, and then it's 6 plus 2 is 8. Okay, that seems to be working. And for some reason it's cut off at the end. It's actually confusing. So let's go check out what's going on. Okay. All right, I think we're running into a Verilator bug, which is annoying. So actually maybe what we can just do at the end is throw on another delay just for fun.
Yeah, honestly, sometimes it gets cut off in like the homework as well.
Really?
Yeah.
It's annoying. Maybe it's a Surfer bug thing. But okay, so let's go and rerun this. Okay, so it ran like instantly, and it's sporting, and I'll reopen this file, and hopefully it is now fixed.
Oh yeah, you know you can you can right click on TV, like on the TV and scopes,
Oh, okay.
and then right click and do add scope, and it adds everything.
That is very cool. I actually did not know about that.
I found that out because I was like, I keep having to tap.
Yeah, that's great.
Oh my god.
Although I don't know why it's still not.
I just do add scope, not add reversible weight. I don't know how to type reversible weight.
But they're also there.
Okay, that is. Okay, it's GTK. It's very small though. Oh, okay, never mind. It looks like it can just.
Getting a second.
What?
Is it because it stops after this?
You need to put a semicolon after TV.
Oh, okay.
Yeah.
Nice.
Mm-hmm.
What was that?
Is it because it stops after the insert?
Well, yes, but I would at least expect it to
Yeah, have a.
And these are
turn this. Wait, I'm very.
Yeah, mine also doesn't have the the third set of values.
Okay, I think we're getting a weird Verilator bug.
We can try having 21 so passive use or error and then see if that works.
Yeah. Alright.
Oh, does it do a seg fault every time the insert fails?
No, it aborts.
No.
Oh, okay.
But I mean, I wouldn't consider an abort to these.
So I will say that Verilator actually just only recently added timing support, so it can be a little buggy. And that's actually one of the reasons why CocoaTB is often preferred for open source verification.
No, you can check them,
I guess.
see if it actually included those.
So actually, so what I usually do. Okay, I'll just show you what I usually do. I was trying to keep it a little simpler, but so anytime I write assert, what I actually do is I do a statement past that where I say like wait for just a little bit extra because yeah, sometimes it gets cut off at the end. So you can do after an assert you can write else, And this will run now like the fallback command if the assert fails.
Instead of crashing and burning.
Exactly. So what you can now do is like fatal, and this will say like, yeah, you can say, I don't know, bad result, something. So we could go and grab whatever the result was. We could say %d. Okay, so now this will print out the value there. Then what we can do as well is actually run each of these fatal commands after just a little bit of time. So we can actually just add on maybe like one nanosecond at the end, just for fun, just to kind of delay things and let things settle and whatnot. So this is what I usually do. And so this should fix it. If this doesn't fix it, then I don't know. You can be mad at me. Okay.
You need to change the 21 back.
I do.
Yeah.
Okay, cleaning up, good. So hopefully this works. So I'll open this up. And is there a way to refresh this?
I think you just have to close the file and reopen it.
You sure?
Yeah, that's usually what I've done.
Okay. There we go. Okay, good. So, yeah, I don't know why it's doing that. Verilator, like I said, can be kind of finicky sometimes. So cool. So now we can see our result over here, and notice that these are all in hex. So I think I can just go and change these to now be in unsigned decimal, which is somewhere. Anyone see it?
Data format.
Wait, is it just cut off at the end?
It should be there. It's been there. Like, I haven't used it for.
Maybe it's just, yeah, there we go. Okay, it's just cut off, unsigned. Okay, cool. So yeah, so we can see 9 plus 12 is 21. And so we can look at this and, maybe we're pouring in, or we've been looking at this waveform for like an hour. We suddenly realize like, oh wait, this seems to be like the problem or something. It's like here it's failing. We can see 9 plus 12 is 21. And maybe we're forgetting this weird edge case because in our test bench, we're expecting it to equal 20. So then we can just go and add our little like edge case right here and say like, oh yeah, specifically for like 9 plus 12. Or I guess we could have made it 9 plus 10, like 21 or something. But that would be this case. Okay, cool. So I will now go and change this to 21. So, fantastic. Let's now, let's make this adder, actually, okay, how much time do we have? Okay. Let's make this adder take multiple cycles now. Actually, okay. I'm trying to think. I went a little slower than I was expecting. I'm trying to think the best way to end out the next part. Okay. Yes. Okay. What I want to do now is I think I just want to keep going with what I had planned. So now, we're going to skip quite a bit ahead. It's going to get a little bit more complicated, or quite a bit more complicated. So here I have a module that I have already written, and you don't really have to worry about what this is, but this was inspired by an assignment that I gave to CSE225 last quarter. Students had to implement this, which effectively what this is it has pins TX and RX. Anyone know what these pins are? Yeah?
It's for the communication.
Yes. Specifically, at what communication? What was it?
UART.
UART, yes. Yep, so this is UART. RX, this is receive. You can see it's an input because we're receiving something. And then TX means transmit because we are sending out something. UART, effectively, how UART works is, you have just one single device communicating to another device. One device will send out data on a transmit wire, and it will be received on the receive port. And in order to just send a message, first you send a 0 to say like, hey, I'm about to start sending data. Then you go and send 0 or 1, depending on if you want to send 0 or 1. Usually you send 8-bit packets at a time. That is how UART works. Not too complicated, but what's nice is because it's so common, what we can do is if we wanted to use UART, we could just go and grab some sort of like open source UART module that will convert the, kind of like confusing incoming like receive packets. And what it can do is it can take in this receive packet and then convert it to a format that we are familiar with. Okay, what is this interface? Have we seen this before? This is a ready valid interface. So this random module that I found on the internet is actually created by like a very popular open source IP creator by the name of Alex Forensic. And and so Alex Forensic made this module that anyone can go and download, and it's over here. Here's the module. You can read through it if you want. I'll probably post a link to it. And this will take in the incoming kind of confusing receive packets and go and convert it into a ready valid output. So then what this module does is it takes in, it receives in packets, and specifically it takes in 8 packets. So it takes in 64 bits of data, and it turns those into 2 separate 32-bit numbers, which it then multiplies together. So what this does, you can see it's called UART mul. What it does is it takes in 2 32-bit numbers over UART, and then will produce the product over UART as well on the TX wire. Okay, that's what this module does. And now the question is, how do we verify that this works? So you can see it's a big step up in complexity versus just like a simple adder. But what I want to show you is a test bench that I've written for this. And potentially, I think we might actually write most of it together. Okay, any questions on what this module does? We need to be like clear on what this module does before I move on. Can you quickly turn to the person next to you and just in like 2 sentences explain what this module does so that we're all on the same page?
It takes in bits 1 bit at a time, and assembles 2 32-bit numbers out of that, and then multiplies them together. But then I think the bits that are coming one at a time are actually from like these 8-bit bytes that are being transmitted at one. Or no, I guess no, it is serial. So yeah, it is just receiving them 1 bit at a time, and then the UART library is probably like handling that and getting rid of like, the marker bits on the beginning and end of the data.
Okay, cool. So I'll say one more time. What this module does is it receives in this single bit of wire, and this wire will oscillate between 1 and 0 using UART. And you don't really have to worry about how UART works, but what it does is it has this library down here, which will magically convert the incoming 1-bit UART signal into this ready valid signal here, which has like this data bus. And so it is able to receive in 64 bits and then produce the product of the first 32 bits multiplied by the second 32 bits. And then we'll send out that product on the TX line. Okay, so I want to now show you the test bench that I have written for this. And I think, we'll start in some ways from scratch. I think we just get rid of all this. Ignore all this. Okay, so here is my test bench. So what is the first thing that we need to do when we create a test bench?
Instantiate your duct.
Yeah, absolutely, yes. So we can now go and instantiate our duct. Good. And so now I'm instantiating this, and sure, let's keep it called UART mul, actually, and I will bring in these parameters. So we have desired baud rates. We can just use default values if we want. I'll just leave it like this. Good. And then we have clock reset, and then RX and TX. Okay, and then we can go and, oops, dang. Then we can go and connect all of these. There we go. So we've now instantiated our DUT. And now the first thing that we need to do after we've instantiated it is now we need to create a clock signal. Okay, anyone who's written a test bench before, anyone know how to create a clock that runs at simulation?
Probably something starting with the $sign.
Yeah. So what we can do is just create another initial block. Oops. Initial begin. And there's a few ways we can do it, but what I'm going to say is we'll say clock I. We can go and drive it, so we can say it's equal to 0. Then we can create a loop, and we'll create a forever loop, which is just like an always true. It's like an infinite loop. So now we can say that we can make like a clock frequency parameter. So we can say like local param int clock frequency is maybe equal to, I don't know, 12 megahertz like this. It's probably fine. I guess it'll match this right there. Cool. We can also grab this desired baud rate and pull this out as well. So now if we want to create a clock that oscillates, so let's for now, let's say like 1 millisecond. Okay, if I now say clock is equal to not clock, so the question is, what will the frequency of this clock be?
1 kilohertz.
Yeah, 1 kilohertz.
Almost.
Oh,
Almost 1
500.
Yeah, so this would be
500.
this would be 500 hertz, right? Because what is happening is, yeah, it's initialized to 0, and then waits 1 millisecond, and then switches to 1. Then, because it's an infinite loop, then it'll wait another 1 millisecond, then it will switch back to 0.
Does the code in the infinite loop get sort of spun out into another thread that keeps running forever, or does your execution just get trapped inside that loop forever?
Right, exactly. So anytime you write an initial block, in a way you can think of it, yeah, as a different thread.
Oh, okay.
Right. Absolutely. So now we can go and make another initial block.
So if you have multiple initial blocks, their code will kind of get interleaved.
Exactly, yeah. So yeah, now we can say initial, we can do kind of basic things, or we can say dump file, we can say this is, sure, make this an FST. So the difference between VCD and FST files, I want to briefly pull this up actually. So I'm going to quickly open up this VCD file in Notepad.
Oh, wow.
So here is the VCD file in Notepad. So this is what like Surfer and this is what GTK Wave sees. And so I can't remember exactly what's going on here at any one time. Yeah, you know what I think it is? I think so here is a wire, and I think it is the wire AI, and it is shorthanded to this hash symbol. So it says AI is equal to this number at time equals 0. And then at like this time, you can see hash now changes to this number. And then at this time, hash now changes to this wire. So it's a very like kind of verbose thing. You can imagine if you have like a really long simulation, or if you have like thousands, even millions of nets within your design, you can imagine that this will be really, really slow, because there are like better ways of encrypting it. Yeah, Mark.
So for example, if we have more wires, like
Mhm.
how would you represent all these different, like, because now right now it's using pound or dollar and percent, like, when does it, how is it going to represent all, like, if we have thousands of wires, something like that?
Yeah, so it'll create like a unique identifier for each one of them. So it might be like pound, 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 or something. I'm not certain. Yeah, cool. So this is a VCD file. What an FST file is it is basically just a VCD file, except I think it is basically just encrypted using some sort of common encryption algorithm.
Encrypted?
Sorry, not encryption, compression. Thank
Okay.
you, compression. It is compressed using a common compression algorithm, something like zip or something.
Wait, so FST is just a VCD zipped?
Yeah.
Oh,
Right.
that's, okay.
So that's actually useful because I think it gets a little bit more complicated than that. But effectively, what FST is it's a compressed version of a VCD file that runs much faster because now it doesn't have to load this potentially 10 gigabyte file. You can see there's going to be a lot of repetition because it's just plain text and it's just a lot of ones and zeros. So there's tons of compression you can get. So you can go from potentially 10 gigabyte file all the way down to 100 megabyte file with FST compression. Cool. Okay. So good. So here, we're creating a FST file instead, and I will also do dump bars, and I'll just pull in some other things. So this is what I always like to start my test benches with: is dump bars or dump file, then dump bars, then a display statement that says begin simulation. Then I set a random seed. Here I'm setting it to 100 for no reason. And then here I'm setting the time format. And then at the end, what I like to do is display end simulation and then finish. And so everything now will happen right here. Okay. And so what we could do now, if we wanted, we could go and start writing out to this Rx input. We could say Rx is equal to 1 or something. Then we could go and wait for some amount of time and then set Rx to 0. And we could bit bang the entire signal. And we could do this over multiple cycles where we send a 0, then we send the 1, send the 0, send the 1. And then eventually that would elaborate out to the full signal. Then we would imagine that our DUT will return back on the transmit port. And then we could go and have a second, maybe block, or a second bit of code that now sniffs out what data is on this TX line, and then it converts that. And then we just have some big assert at the end that's assert that this input signal times this input signal in fact does equal the TX thing. And we could do that, but instead what is very common is having helper tasks. And a task is just a function, except, there's two words for functions in Verilog. A task is a function that can take place over a span of time. So what I'm going to just paste in here is first a reset task, just to show you the syntax. So here is a task, so it's automatic, you can ignore that. So this task is called reset. And what it does is it sets the reset line to 0, then it waits for a pause edge of the clock. So it waits until the pause edge happens. Then it waits for some extra small little amount of time. Then it goes and deasserts the reset. And so now I can go and call reset here. And there we go. So now, this will properly go and reset our DUT. Now we can actually begin working on it.
Why did you have to use the different assignment operator?
Oh, I don't actually think there is a reason. Yeah, there's no reason. Verilator is really bad at telling them apart anyways, so I think you're supposed to always, actually I can't answer that.
Okay.
Honestly, it's a little finicky, so sometimes I just go between them. Test benches are less kind of particular in the way that you write their code as RTL is. Yeah. Okay. I'm going to post in, does reset make sense? This is good. Okay. I'm going to post in this new task, which is much more complicated, but see if you can absorb it and see if you can explain what is happening to the person next to you in this task. Reset is active low, so it's only activated when it's 0. So this will actually deassert because it's,
Why is reset active low so common?
Because of NAND gates. I can't answer that right now, but
It's just transistor stuff.
yeah, Yeah, it's like logic stuff, yeah. Yeah, like,
One of the labs, I was having a problem where my thing would only work after I reset, because I had like a reset.
Oh, that one's supposed to use a default, it stores in the value originally, and then it loads it in of the order. And that way you can have it originally reset. So it succeed in the shipment.
So would it not be a problem if it was active low reset? Or would it still happen?
No, it's
Still happen.
yeah, the only difference between active high and active low is just like, with what value the reset is activated. They don't behave any differently though.
I just thought because it's off in the beginning, right? Is
Mhm.
everything low at the start? Like, don't you start in the reset case instead of in the not reset case if you have to go? Or is that not how?
No, there's no difference. Like if I wanted, I could, by default, I could say reset is equal to 0 here. This means like starting out, always reset. Or I could say starting out, just make it kind of like not reset.
Does Verilator do high impedance and disconnected or not?
It does not. So it just converts all of those to 0, but you can also specify it to have it interpret it as like ones, or you can have it interpret it as a random integer. But by default, it will interpret all x's and z's as 0. Yeah. Okay, cool. So here's send byte. What this does is here it constructs a UART frame. So here, like, it's kind of backwards actually, because UART kind of sends things kind of backwards. So this 0 right here, this is actually the first thing that is sent. This is the start bit. Then it goes and sends all of the other data bits, but it sends them like backwards down the line. Then it ends with this stop bit. And you can also notice that that's what's happening because we start at index 0, which is like this position right here.
Oh, Verilog arrays are backwards?
Yes, they are backwards.
Oh.
Well, because I specified the order right here. So I'm saying that...
Wait, can you do 0 to 9 and then it's like...
Exactly, yeah. So if I did
Oh.
0 to 9, then now it would be
But then you'd have to
actually
reverse the
backwards.
data.
Yeah, so now I would have to say like is equal to 10, and then I'd say like
Oh.
not equal to 0 or something. Yeah. Yeah, but like honestly, most tools can't actually support that, and they just always assume that all arrays are backwards. Yeah. It's a lot of ifs, ands, and buts. But there we go. Okay, cool. So this is our UART frame. So yeah, here's our start bit. Here's our data. Here's our stop bit. Then it goes and sends each of the data. And here it delays it corresponding with how much delay we need between each like bit of data being sent. Like I said, like what UART does is it will just oscillate between 0 and 1, depending on if it's sending a 0 or 1. But those oscillations need to happen at a like specific pre-specified rate, which is called the baud rate. So here we're saying like, yeah, wait for the correct amount of delay in order to properly produce this baud rate. And in this case, the baud rate is 9,600 like flips per second. Good, okay, so that is send byte.
Is the baud rate connected to the clock rate at all? Or, no, I guess it's absolute, isn't it?
So generally they are disjoint. Yeah, the ideal is no matter what clock rate you're at, your hardware should work for any baud rate that you give it.
Oh,
Yeah, specifically,
wasn't there a set of like standard baud rates?
Exactly, yeah, there's a set of standard baud rates. So now what we can do is go and send some bytes. So I have all of these already written out here. So what I can do now is send 0003 and then 0006. And this is being sent, I guess, as big endian, which is maybe a little bit confusing. So in total, this value will be like hex 00000003. Is that right? 2 zeros? Yes. Hold on. 0000. Yeah, 003. Okay. That is this value. And then this value will be 6. And so we should imagine now that after we've sent each one of these packets, that it will now convert into the product at the end. And we can go and confirm this by just putting like a really big delay at the end. Maybe we can say like delay 1 second, and or maybe like 10 milliseconds, so it's not as long. And good. So let's go and run this, and hopefully this will just work. So do we make
You did not print out anything, unless you're just gonna do on the waveform.
print? Oh, it's just gonna look at the waveform. Yeah. So okay, cool. So it looks like it properly did send each of the bytes.
So why do you have to wait 10 seconds? Or will it just stop
Oh,
when it's
'cause-
finished without waiting for everything to like equalize?
I'm just waiting for it to respond back with the data serially after that.
Oh, that makes sense.
So good. So now I can go open, say GTK, or I guess I can do it in Surfer. Fine. So I can open this dump.fst. Hopefully this works. So I'm just adding everything. It's taking a while. Cool. Okay. Hopefully this is good. So we can see. Well, here's something. Actually, I don't know if I like this.
You shouldn't have done recursively.
Yeah, I actually
Yeah,
don't.
it's do regular apps too, I
If you,
Can I just add? Oh, add scope.
Yeah, you-
Nice. Okay, this is much better. Cool. So good. So now we can see that. Is it properly getting the data? Yeah. Okay. So here is RX. So RX, if you remember, so this is all of the data that's being sent in sequentially. Right. This is one single bit, and yeah, it looks like we are in fact being like sent this data, and this looks like a 0 that we're sending because like for most of it it's 0, and then finally at the very end we get a stop bit. Then it's sending more, like 0 because it's all zeros. Then it's a stop bit, more 0, stop bit. Then here it's sending 3, and then the rest zeros, stop bit. And then it's sending 0, 0, 0, and then this looks like it is 6. I think. So now it, in theory, is processing. It's processing, and now we should see. You know what? I guess we don't see TX for some reason. That is disappointing.
did you tell it to transmit? Do you have to tell it to transmit?
Wait, why did it? All right, it's always something not working. This is the issue with like relying on live demos in my lectures.
Yeah, but it's way more fun.
Well, I guess class has kind of ran out, but so we can return with this. We'll definitely spend a lot more time on test benches. But hopefully this was at least a cool kind of introduction to like how people kind of write test benches when trying to verify hardware. I'll kind of end with this final thing, is that actually I think the statistic is that 80% of all chip design time, like 80% of the cost that goes into designing a chip, specifically in like towards engineer salaries, is like all goes towards verification.
Oh.
So only 20% is actually used for the construction of the modules, and then 80% is for verification. And this is because like you really want to make sure that your chip works before you spend potentially like $1 billion sending your design to TSMC, because you say, TSMC, hey, like I would like you to put this on your most cutting edge 2 nanometer process. And TSMC is like, that's fine, but like we don't have a 2 nanometer process yet. So you like giving us that money will actually make us that process. And so you give them $2 billion or something, and then you realize, oh, whoops, I should have added one more test bench because my chip didn't work, so now I'm out $2 billion. This happens from time to time. It's very rare, but it does happen.
I like the Pentium thing or
Yeah,
whatever.
the division unit in the Pentium processors is probably the most famous example. Yeah, okay, Leeway.
Can you post today's code? Like you don't have to post like the UART, but maybe like the earlier stuff that you did.
Absolutely, yeah.
Honestly,
So,
I think it'd be cool to see.
I actually will post the UART as well. This is actually just a Git repo that I've already written.
Okay.
Yeah,
And could you also post Wednesday's code?
yeah, and I am behind. I'll post all the
No worries.
code. Yeah. All lectures have been posted though on YouTube.
Okay. I
Yeah,
forgot.
but I will post the code after class.
Okay.
Yeah. Okay. Enjoy your weekend, everyone. I will see you on Monday.